Hooray. Okay. All right, hello. I'm John, and I'm going to be talking about some work in progress towards a categorical model of Lilac. This is joint work with my advisors, Amal, Ahmed, and Stephen Holtzen at Northeastern, as well as my collaborators, John Aytac and Philip Johnson-Freyd at Sandia National Laboratories. So before I start going towards a categorical model, I just want to explain what the model is that we're going towards. So let me first tell you about Lilac. Lilac is a probabilistic separation logic, which means that it's a separation logic for reasoning about probabilistic programs. So ordinarily, we think of separation logic as reasoning about imperative programs, right? So for example, if I have a program that allocates 2 memory cells, I can assign it that postcondition shown in purple, which uses this substructural separating conjunction to assert that the heap locations governed by the variables x and y are like disjoint. Right? They're non-interfering chunks of the heap. In a probabilistic separation logic, we use this substructural conjunction to now mean probabilistic independence. So for example, in Lilac, if I replace that program with a program that generates 2 random booleans, then I can give it this postcondition, which uses the separating conjunction now to mean that the x and y are independent random variables. And Lilac is a particularly nice semantic model of a probabilistic separation logic. So we show that every independence relationship can be expressed as a separating conjunction. So in some sense, it's like complete for independence. And we use it to verify some fun randomized algorithms. If you're interested in the details, you can check out our PLDI paper, which came out last summer. And the main idea of Lilac is that you want to kind of split probability spaces. So just as separating conjunction for ordinary separation logic holds of a heap if that heap can be split into 2 disjoint subheaps, Lilac separating conjunction holds of a probability space, which is a pair consisting of a sigma algebra and a measure, if it can be split into 2 subspaces. And then just like how ordinary separating conjunction is interpreted by disjoint unioning these heaps together, Lilac separating conjunction is interpreted by this operation that we cooked up on probability spaces, which we call independent combination, and it just basically independently unions together probability spaces. Okay, so this is a very nice picture, but there's quite a bit of fine print. For example, the proofs are a little longer than you would expect if you crack open our PLDI paper. This is just showing that independence is associative. It doesn't seem like it should be that hard. And if you look at our main result, which is like the final semantic model we use to interpret propositions, there's a lot of side conditions hanging around. Like things have to be countably generated. There's this thing, finite footprint, I don't know what that is. Things have to be extendable, right? And there's this weird Hilbert cube, this weird sample space. And what's kind of bewildering about all this is it's not clear which of these conditions is essential to getting a model of probabilistic separation logic, and which of these conditions is just something we had to throw in to get the proofs to work, right? And that makes it kind of difficult to generalize Lilac to support, fancier features. That makes it difficult to abstract it, kind of apply it to other settings, and so on. And I think this complexity is especially bewildering. If you're familiar with the notion of probabilistic independence, it seems really simple, and I think an obvious question to ask is why isn't separating conjunction about product spaces, right? So, for example, in a probability theory class, maybe you want to model 2 Boolean random variables. They're independent. So you can construct a sample space, which is a product space of the set of Boolean values with itself, and then you can set your random variables to be projections out of this space. And clearly, those random variables are independent, right? So why did I need all this weird measure theory to get Lilac to work? I think this is a very natural question. I was asked variants of this question when I presented preliminary versions of Lilac at last year's LAFI. I was also asked versions of this question when I presented Lilac at PLDI. And both times, I just kind of didn't really have an answer. Actually, the truth is that I spent a lot of time trying to get product spaces to work for separating conjunction, and it just didn't seem to validate the inference rules that I needed to reason about the randomized algorithms I wanted to reason about. But today, I have a more optimistic answer, which is that Lilac's independent combination actually just is about product spaces, as long as you coerce everything up to the right equivalence of categories. So to explain this, I first need to explain some history. So let's go back to ordinary separation logic. So nowadays, ordinary separation logic, separation is heap disjoint union. But it actually didn't used to be that way. In fact, some of the earliest models of separation logic, actually precursors for separation logic, didn't model separation this way. They modeled it as this construction on functor categories, defined in terms of this thing called deconvolution with respect to a coproduct on a category of store shapes. And this whole construction kind of lives in a whole category of functors. which is called the Chenuel topos. I put an asterisk there because this is, strictly speaking, K is not actually the Chenuel topos, but it's basically the Chenuel topos. And I think there's a very natural question once you see this for the first time, which is like, what in the world does this day convolution have to do with the disjoint union-based model that I know and love, right? And what's cool about this setting is that there is a very nice, crisp answer to this question, which is that the day convolution is the disjoint union, as long as you coerce everything up to the right equivalence of categories. In particular, there's this old book on topos theory, and inside that book there's a theorem that says that the Chenuel topos is equivalent as a category to the category of nominal sets, which are this tool that people use to reason about syntax with binders, programs with local state, and so on. And if you inspect this proof and how it implements this equivalence, you can further show that the day convolution used to construct separation logic corresponds across the equivalence to the familiar disjoint union of stores model that we all know and love. Okay, so back to the present day. I have this question, and I propose this answer, and my answer has exactly the same structure, basically, as what I just showed you in the previous slides. So we're going to construct a category, which is basically a probabilistic version of the Chenuel topos. We're going to construct a category, which is a probabilistic version of nominal sets. We prove that they're equivalent, and then we inspect how that equivalence works, and if you carefully calculate, you can show that the day convolution in the probabilistic Chenuel topos corresponds across the equivalence to Lilac's independent combination, modulo some side conditions. Okay, so what does this give us? Well, first of all, it shows us that the naive, informal pen and paper notion of probability is right. If you do enough category theory, this really nice picture can be your model of separation. And it also shows that independent combination is also right, because they're the same. So this kind of validates Lilac's notion of separation, and it kind of tells us like which parts of Lilac were kind of essentially getting separation to work and which parts were just contingent aspects. And more interestingly, it kind of corroborates a lot of recent work that has come out, connecting like the semantics of probabilistic programs to the semantics of programs that manipulate local names. And I think that our result, which is kind of like a probabilistic version of an old theorem from the theory of names, is like further evidence in this line of work and provides interesting nominal interpretations of probabilistic concepts. So if you kind of look at our equivalence of categories and you look at like what the corresponding things would have been in the nominal situation, you find like this table of correspondences between concepts. For example, like the notion of a measurable space in probability theory ends up looking a lot like the notion of support in nominal sets. And I think this creates a lot of interesting potential for future work, because there's a whole line of research about like applying nominal techniques to reasoning about things like local state and syntax with binders, and now maybe we can do the same to reason about probability. So I have a lot of details that I left out of this talk. If you want to see precise definitions, precise theorems, please come talk to me. I am happy to overload you with weird definitions. If you want to see more details, there are some in the extended abstract on the top right corner. And of course, feel free to shoot me an email with questions. Thanks.